I'm here to help you out with the suggested homework problems number 15.43 and 15.63. This is all covered in section 15.3 in your text, and it will help if you read that. So let me kind of just lay out the land here. I have two graphs here, and one of them refers to first order decay, and the other one refers to second order decay. And just so you get kind of a sense of what's happening here, what I'm graphed here is time on this axis and the concentration of some substance, A. I'm thinking about a reaction that goes like this. A decays to products. And so, of course, it starts off, A concentration starts off at some value given by A naught, and it gets smaller over time. That's true for both first order decay and second order decay. We have an integrated rate law for the first order. You know this from your Excel sheet. It says the concentration over time equals the initial concentration times e to the minus k1t. And what I want to tell you about in this video is how the half-life figures into all of this. So here's how you figure out the half-life from a graph. We say that's the starting concentration. I would go down to half that concentration, and I'm going to draw a horizontal line, and goes off to here, and then I read down here. And, well, this is the amount of time it took for the concentration to go down to half its initial value. So we would say this time interval, that's the half-life of that decay process. There's a relationship between that rate constant and the half-life. It's given by this equation right here. It says that they're inversely proportional. That is, if I made k bigger, that means the half-life would be smaller, and I'd have a curve that decays quicker, as you saw from your Excel sheet. That is equation 15.23 in your text. Now, there's an interesting aspect to half-life decay for a first-order process, and it goes like this. What if I was thinking about that as my initial concentration, and I say, well, how long does it take for you to get to half of that value? Well, I would go to about half of that value, cut across the line here, and point down. And look at this. The second half-life, T1 half, that second stage, is equal to the half-life of the first one. And that's kind of obvious, I hope, from here. The half-life of first-order decay doesn't even know what the initial concentration is. There it is. It's just 0.693 divided by the rate constant. How about for second-order decay? That's what this graph is all about. I've also drawn a curve here. There's the initial concentration. There's time. As you know from Excel, the integrated rate law, that's the integrated rate law for second-order decay, follows this equation. And the thing to note about this is that decay process, the concentration of A over time, it depends on what the starting concentration is. Let's see if we can piece together just graphically what the half-life looks like in this case. How do we do that? Well, I'm going to once again go to half the initial concentration and draw a horizontal line. And there we go. There's the half-life. There's the first half-life. Okay, it takes that much time. How long does it take for this initial concentration to go down to half its value? Well, I go to half its value right there, and if I've done this properly, I go way out to here, and I see, oh my goodness, the second half-life is a lot longer than the first half-life. That's shown in this equation here, which is, I didn't write it down, that's equation 15.28 in your text. 15.28 in your text. And it says this, the half-life, how long it takes for it to the substance to decay to half its initial value, equals 1 divided by the initial concentration also divided by K2. That's the same rate constant that appeared here. So in particular for homework problem 15.43, the question says, if you double the initial concentration of something, what happens to the half-life? Well, I can see what happens if I make this number twice as big, the denominator's twice as big. That means the half-life is half as big. It reacts faster. For the second part, problem suggested homework 15.63, the way I would like you to solve that problem is you're given some data in the problem, and just as you did in Excel, set up the whole thing in Excel, set it up as a second order decay process, and you can mess with the K value, the K2 value, until you get a good match with the experiment. That's how you do it. And if you want to then, after you've done and you found the right value of K2, you could put it into this equation here and you could calculate a half-life. And that's probably a good exercise to do.